So we just talked about continuity, what our requirements are. We need a defined y value, a limit that exists at that x value, and our limit and our y value need to be equal to each other. So we're going to be looking at this piecewise function. So we're going to determine whether the function of f of x is continuous at 3. So the first thing we need to talk about is a piecewise function. So this is what is called a piecewise function. It takes pieces of certain equations and sticks it together based off of these conditions. So our conditions are all around that value of 3. So if we look at x equals 3, we are going to look at that middle piece here, that function of 9. If x is less than 3, so anything before 3, negative 0 to all the way up to 3, we are going to be using this function right here. And if it is beyond 3, greater than 3, then we are going to be using this function down here. So depending on what we need to look at, tells us what function we are going to look at. So the first thing we are going to start with is just f of 3. So f of 3, well, 3 is our x value. So if we look at our function, when f of x is 3, we are going to be using that y value of 9. So the really nice thing is that's super easy for us. So f of 3 equals 9. Now, because we have a piecewise function, and specifically a piecewise function where things that are less than 3 and things that are greater than 3 use different equations, we have to look at the left and right limits separately. So we're going to look at the left limit first. So the limit as x approaches 3 from the left of f of x. So we have the limit as x approaches 3 of. We are looking at the left, so we're looking at numbers less than 3. So we're going to be using that x squared minus 9 divided by x minus 3. Okay, so if I do my quick check, 3 squared is 9, 9 minus 9 is 0, 3 minus 3 is also 0, so we are going to need to do something else, because that gives us indeterminate form. It has a squared, so I'm going to try factoring. X squared minus 9 is very special. It's a difference of two squares. Difference of two squareds will always give me the same kind of setup. So when we have the difference of squares, we are going to have whatever we have the two terms unsquared, so square rooted, one adding those two together and one subtracting those two together. So if I were to try to factor this using any of the other methods, we're going to get the same factors, just it might take a little bit longer. So knowing kind of some of these shortcuts is what gives us that extra time when we need it. So x squared minus 9 is x plus 3 times x minus 3. We have an x minus 3 in the denominator, which is really good for us because we can go ahead and cancel them out. So we have the limit as x approaches 3 from the left of x plus 3. Now that we have something that won't give us indeterminate form, we're going to go ahead and plug in 3. 3 plus 3 is 6. Okay, now you may be sitting here thinking, but what we got for our y value is 9, and we just got 6 for our limit. You are correct, we did just get 6 for our limit for our left side. But our second condition isn't asking, does our limit equal our y value? It's asking, do we have a limit that exists? So even though I know something is wrong because these are two different numbers, I am not at the point where I can say that it's not continuous yet. So we need to look at the right limit first. Okay. So the limit as x approaches 3 from the right of f of x means that we are going to look at our function when x is greater than 3. So we're going to be using x squared minus 3. Okay, thankfully this one doesn't have any sort of issue, so I'm going to go ahead and just plug 3 into this function. we get 9 minus 3, which gives us 6. So the thing that we now know is that our left limit and our right limit give us the same thing. This tells us that our limit at x equals 3 exists and it equals 6. So now we can say, hey, f of 3 does not equal the limit as x approaches 3 of our function. And we know that for sure because 6 does not equal 9. So now that we have made this statement, we can say f of x is not continuous at x equals 3. So if something is not continuous, we almost want it to be not continuous right at the beginning. So if we can have something where our limits don't equal or our y value doesn't exist, it's going to go faster. But we do have to go through everything in order to kind of make that decision. So I had a y value. I have a left limit and a right limit, and they are equal to each other. But our limit and our y value don't equal. So we had to show every single piece of this in order to clearly explain that with this definition. So this last one is a little bit different than just deciding if it's continuous. We want to determine the value of k that makes our function continuous. So things that we need to know is when we look at this piecewise function, when we are at 4, we are using whatever coefficient or constant that we are trying to find. So f of 4 is something that we can't really solve for, but I'm going to write it down anyways. On the other hand, we only have one other function. We use that whenever x is not 4. So that means every other moment in this function's life, besides when it is equal to x equals 4, we use that top function. So I'm going to just start with our y value. F of 4 equals k. We don't know what it is yet, but we can figure that out in a second. Okay, now we need to look at the limit as x approaches 4 of our function. So we're going to be using what our lines are approaching. So because a limit is not what is the y value, what it's approaching, we're going to be using anything that is around 4 but not equal to 4. So we're going to be using this equation up here. I only need to check x equals 4 because it is a stipulation over here, but also if I were to plug in 4 into the denominator, that makes it undefined, or 0 in the denominator, so that would also make it not continuous. But we are looking at the same thing. So our function is x squared minus 3x minus 4 divided by x minus 4. Okay, if I plug in 4, 4 squared is 16, and I'm going to subtract 12 and another 4. So that's already going to be 0, and we get 0 in the denominator. So we are going to try to factor it the best we can. So the limit as x approaches 4 of... So the good news is I know x minus 4 has to be one of my two things. This is also an x to the 1x to the first power, so I know they both have x's. So we need to figure out what multiplies to negative 4 but adds to negative 3, which happens to be negative 4 and 1. So x minus 4 and x plus 1 are my factors. So we are looking at the limit as x approaches 4 of x plus 1 because we can go ahead and divide out those x minus 4s. So now all we have to do is plug it in. So we have 4 plus 1, which gives us 5. So the nice thing here is we know what our limit is. We didn't have to check left and right. We just have our answer for our limit. So now that we have that, we have a last situation. So we have f of 4 has to equal the limit as x approaches 4 of our function. Well, we know f of 4 happens to equal k. On the other hand, our limit happens to equal 5. So we know that k has to equal 5 to be continuous. This is not necessarily required, but we're going to just go ahead and wrap up our answer. It's kind of like we showed them all the work, now we're going to explain what we were talking about. So to be continuous, k needs to equal 5. So in order for f of x to be continuous, k needs to equal 5. Okay, so this is kind of like our continuity at a point. Sometimes they may ask us what would make something continuous, which is still using those three things. On the other hand, if we are looking at graphs, we can kind of make some ideas. So these different things have different names. So when we talk about a removable discontinuity, it is anything where we are missing a point. So if I have a hole somewhere, so I could have a hole in a graph, this is technically removable because we have removed a point, or if I have a solid point in there as well. So it's like removing it from where it was originally and plopping it somewhere else. A jump discontinuity is when anytime we have a break. Sometimes this one is called a step discontinuity, but a lot of times people call it a jump discontinuity. And it's called that because of this space. It's like if you were to walk along here, you would have to jump to get to that next place. And they call it step because if it was going the opposite direction, you might have to step down to get there. Our last one, infinite discontinuity, is when we are talking about a vertical asymptote. A lot of times it's something that looks like this, where we have a certain value that would give us that vertical asymptote. This is that infinite discontinuity because it's going towards infinity of some sort. Okay. In our next video, we're going to be talking about our theorems and kind of go through some stipulations, what they mean, things like that.